Fluids are important, and here's where water comes in. Remember how we said water was so important when we were weathering materials and making soils? Same thing here. Water speeds up chemical reactions. It carries ions into the mix. It carries waste ions out of the mix. Creates fresh surfaces so chemical reactions can occur. So water is really important. And parent rock, of course. I can only make so many things out of the beginnings. I can't make gold out of fleece. Those kind of things don't work. So obviously what I start with is going to be critical. So if I wanted to go out and find a pile of metamorphic rocks, where would I go look? Well, we know from looking at igneous rocks that almost every continent has a central core to it, just like we have the Canadian Shield, what we call the Precambrian Craton of North America. And you have this area up in here. So does Greenland, South America, South Africa, India, Australia, bits of the Baltic, parts of Siberia. All these areas are igneous shield rocks. Where would I look for metamorphic rocks? Well, I want to find areas where rocks are either deeply buried or where there had been mountain building episodes, what we call orogeny. And in those areas, I would expect to see elevated heat and pressure in these collision zones. Well, where are the mountain belts? As you might expect, the Cordillera, or the Rocky Mountains of North America, the Appalachians, the Andes, the Alps, Himalayas, the Great Range, Dividing Range in eastern Australia. These are places I'd go look for metamorphic rocks. If I'm going to build mountains, you can bet there's collision going on and heat pressure's being elevated. Oh, so here we go. True and false clicker question. Okay, according to Bowen's reaction series, felsic rocks, those rich in silica, will melt at shallower depths than mafic rocks, which are rich in iron and magnesium. What do you think? This is kind of a review of our igneous stuff, but it also now kind of goes toward our metamorphic issues. Clicking by 20 seconds here. 18, 19, and 20. Okay. True. Yeah, and why is that? First, where's the felsic stuff? Down here, right? Cold end of Bowen's reaction series. So as I start elevating temperature, the first thing it's going to encounter are these rocks. That's going to be the first to melt. The high temperature stuff like olivine, calcium, flash, that's going to be the last stuff to melt. So if I'm in a situation where I'm trying to metamorphose rocks, what do you think is going to happen to rocks that are the silica-rich rocks? They're going to start to metamorphose before the ones at the top of Bowen's reaction series, aren't they? Because, in fact, I might actually melt some of this stuff down here before I change the stuff up there. So now I'm going to have another kind of rock we're going to have to talk about, which is kind of an ultrametamorphic rock, where I've melted part of it and not melted part of it. It's going to be a mix of igneous and metamorphic. And you can see right here why that might occur, because of the difference in melting temperatures between felsic and ultramafic and mafic type of materials. Okay. Well, we talked about there's 6 different ways of producing heat and pressure changes. And we can have contact metamorphism right around batholiths when they're being emplaced. We can have hydrothermal fluids that are hot fluids moving through the rock. Big regional structures, mountain building episodes, convergent plate boundaries, or even just burial. I just keep dumping sediments into a basin, and eventually the stuff at the bottom's going to have the most pressure on it from the overburden. It's going to get the most temperature. And we're going to see just confining pressure from all directions. Certainly going to be different than regional type of heat and pressure. I could have faults where there's a sudden break in the rock. Or how about a meteorite impact? Nothing like a good old meteorite impact to stir up the data. Okay, well let's look at contact metamorphism. Remember when we were talking about a batholith or a stock being placed? And we talked about how it's going to bake the immediate surrounding host rock or country rock. And the melt right in contact with that host rock would actually cool off a little bit and we get a chill zone. Well, that's kind of what we're seeing in this metamorphism here, this bake zone idea. Here you can see this intrusive rock that came into this fracture and look at the metamorphism of the country rock that's occurred all along that edge. That's the bake zone. So talk about elevated temperatures. Probably this stuff's being moved in under pressure. So what an ideal area for metamorphism. So I might see some metamorphism right along the edges of the batholith. But to be termed a batholith, it means it's exposed at the surface, right? We have to expose more than 100 square kilometers to call it a batholith, less it's a stock. So to get this exposed at the surface, what happens to all this rock, this host rock? It's eroded away, isn't it? So we don't see a lot of this, because a lot of this is gone. It's just where it survives here and there that we see that kind of metamorphism. Unless we've got the batholith unexposed, then we wouldn't call it batholith, it's still pluton. In this case, it would be fairly limited to just the bake zone areas. A little wider spread would be where we have hydrothermal waters moving through. Groundwater is cold and dense, making its way down through cracks. As it gets near magma, or gets even just heated up by the geothermal gradient as we go deeper, it starts to precipitate minerals, it starts to dissolve other minerals. A lot of times these chemical reactions are being controlled by temperatures. So the other thing that's happening is as that water heats up now, it becomes less dense, and now it starts making its way back to the surface. So we kind of have this cycle of cold, dense water coming down, heating up, and warm water, hot water, going back up. And in the process, changing the immediate surrounding chemistry. So we've got a lot going on with warm water, heat water, ions running amok. Boy, I tell you, we've got perfect conditions for metamorphism there, don't we? So hydrothermal situations oftentimes produce metamorphism. And of course, regional metamorphism. Now here we're talking big areas like half of the United States smashing into Europe, kind of regional basis. And here we can see a subducting plate here. We've got a continent overriding an ocean basin, and that oceanic plate is subducting. And we've got a lot of igneous activity going on here as that plate melts and recycles in the form of volcanoes. But look what happens as we continue to subduct this ocean basin. The ocean gets smaller. It's going away. We're subducting it. And what's looming over the horizon is another piece of continental crust, the other side of that ocean basin, that's moving toward our continent. And eventually, as we continue to do that, we end up subducting all of the ocean crust, and now we have continent-continent collision. So we've got two granitic blocks with collision, and neither of these guys want to subduct. Before, the oceanic plate would subduct. It was the densest, being basalt. But now we've got two granitic plates trying to fight it out, and both of them are light continental plates, neither of them wanting to subduct. So we see what's happening here at the subduction zone changing. we're losing our subducting plate. We don't have anything to melt because nothing's going down there. So we're basically ending volcanism and igneous activity, and we're replacing it with collision of continental crust. It's like a big front-end car crash. So instead of subducting anything, that process is finishing up and going away. Maybe a few plutons coming up as kind of the last gasp. But what we end up doing is building these big mountain ranges as these plates collide, and we shift over to heat and pressure and metamorphism. Whole different type of rock style now. This is exactly what's happening with the Himalaya mountains. And we can measure every year how much they're growing as they continue to collide. Okay, took your time. We'll have to wake up now. Okay. Metamorphic rocks subjected to contact metamorphism will most likely be associated with what kind of environment? Spreading ridge, batholith, deep ocean trench, all of the above. Plenty of time to think about that one. It's kind of split here between B and all of the above. Well, B would certainly make sense. I've got hot magma being injected into host rock. I'm going to get that bake zone. There's contact metamorphism going on there for sure. A deep ocean trench. Well, I've got subduction going on. But with subduction, I've got melting. I've got that melt coming back to the surface in the form of volcanism. Is that metamorphic or igneous? Igneous, isn't it? Not much metamorphic going on there. And the spreading ridge, well, here I've got two plates moving apart. I've got a rift valley system being filled with igneous material that's becoming new ocean crust. Again, an igneous, primarily an igneous process. So, B, batholith is our right answer here. One type of regional metamorphism that you might not have thought about is snow turning into glacial ice. Glaciers aren't freezing out in the ocean. They aren't lakes that are freezing over. The phase change from water to ice as it freezes. Glacial ice is compacted snow. And as the weight of the snow simply keeps compacting the lower portion of the snowfall, it recrystallizes. The grains change. They go from these nice little snowflakes to kind of this granular snow. The arms kind of disappear. It becomes more of a kernel, what we call firn, and finally it becomes glacier ice, where the ice is simply recrystallized, each crystal growing into its surrounding neighbor. And that's why when you see glacial ice, you can tell glacial ice because you look through it and it has this gorgeous deep velvet blue kind of color to it because of this recrystallization. So this is a metamorphic process. You can kind of see that here in these wolf prints. This is up in Siberia, and this wolf ran across this snowy field. And where the wolf stepped, that increased the pressure. His weight compacted the snow there and momentarily increased the pressure and the temperature where it caused just a smidgen of recrystallization of those snowflakes into firn, into ice. Think about it, when you go out here in the snow and you step and you leave a footprint, you're kind of doing the same thing, right? And now the wind comes along, it blows off all the light fluffy snow, and what's left is this partially compacted ice or firn of the footstep. So instead of being deep into the snow, now it stands out more resistant than the snow. So it's kind of the first stages of some recrystallization going on. So, true or false? Would you classify glacial ice as a metamorphic rock? The water into ice. We're taking snow and compacting it, subjecting it to heat and pressure increases, and recrystallizing and changing it. It's definitely a metamorphic process. So yeah, I would call glacial ice a metamorphic rock. What about ice that freezes over along the brook down here? Would you call that a metamorphic rock? No, why not? Yeah, it didn't go through a metamorphic process, did it? It was just water chilling down and going through a phase change, becoming a solid. But it wasn't anything that metamorphosed. Okay, so glacial ice, it works, but other ice, no, it doesn't. Okay. Type number 4 is burial metamorphism. Here we're just filling up a basin with sediment, piling more sediment on top of it. That's weight. That's overburden. And that weight is going to swish down the lower sediment, compact it, get rid of the void space, squeeze the water out of it, and it's going to start on its way to becoming sedimentary rock through the lithification process. Eventually it'll get there. But if I keep doing this, not only am I going to take it to a sedimentary rock, but I keep upping the pressure, upping the temperature, and I'm going to take it beyond sedimentary rock, and I'm going to make it into metamorphic rock. So where's that kind of break point? Well, you'll see that it's between the sedimentary rock shale and the metamorphic rock slate. We'll come back and take a look at that. Fault plane metamorphism. Here you can see we've had an earthquake. Big fault. One block of rock is shifted next to another block of rock. And if you look right along the fault plane, there are going to be little chunks of broken up rock. There's going to have been increased heat. You know, take your hands and rub them together. Everybody do that. What's happening? Your hands are getting hot along the palms, aren't they? Anything happening on the back of your hands? Nah, they're staying pretty cold, aren't they? So, if you think of a fault as being this big friction-generated fault that's slipping one block past the other, you've got heat and pressure that's really pretty intense right along those surfaces. But you get just a little far back into the rock mass away from that surface, just like the back of your hands. Did much happen? No. So this is going to be a real localized event right along the fault plane, right along the break. And here you can see some of it. You see the little pieces all broken up. This is the host rock here. You can just see how that slipping has just smashed up and crushed up the rock right along that movement surface. And cements have been generated to glue it all back together, heat and pressure. But boy, it doesn't get very far away from the fault. Okay, so we're going to talk more about faults a little bit. In shock metamorphism, nothing like a good old asteroid. When we see an asteroid hit, one of the ways we can tell that it was an asteroid, besides looking for the obvious crater, oftentimes, believe it or not, we don't see the crater because erosion and weathering have kind of done their job on it, and it's weathered the peaks and the rim,